Okay. Last time we left off with this, talking about figuring out what carbocation rearrangement will occur, if any. And we saw that, let's see, in this example, we had three possible things we could rearrange, or three possible ways we could rearrange. We could move one of these hydrogens over. We could move this hydrogen over, or we could move that methyl group over. We've tried all of them and figured out that only one of them moved or changed our carbocation from a secondary to a tertiary. Okay, and that's the one that, so that gives us a more stable carbocation. And so that is a valid carbocation rearrangement. Okay, so let's apply this now to SN1 and E1 reactions. Okay, so these rearrangements are going to occur in between the loss of the leaving group and the nucleophilic attack in SN1, for example. Yes, it's the first one that I have. Okay. Okay, so for this reaction, let's do an SN1. Okay, so first step in SN1 is loss of a leaving group. Okay, so we're left with a carbocation and Br minus. And then, okay, so now we've got a secondary carbocation, right? So we should look at the possible places that we can rearrange things. Much better. All right, so hydrogens or methyl groups that we could move include that hydrogen, one of these methyl groups. Okay, they're both the same, but we'll use this one for practice. And there's three hydrogens down on that carbon, and so one of those could move as well. Okay, what should we migrate in order to improve the carbocation stability? If we do the hydrogen on the right, that will give us a primary carbocation. So that doesn't improve the stability. If we move the methyl group toward the carbocation, that's going to give us also a secondary carbocation. But if we move this hydrogen toward the carbocation, let's see. Okay, so that puts that's our hydrogen that's migrated. And now our positive charge is on the carbon that the pink hydrogen used to be attached to. There's our positive charge. Okay, and that is 1, 2, 3. It's got three groups on it, so that is a tertiary carbocation.
Could you show real quick what it would have looked like if you moved the methyl group?
Yes, let's do that. Let's see. So if we moved the methyl group, all right, so methyl group moves there. Okay, so the CH3 has now moved there, and so our positive charge is where the methyl group used to be, which is right there. Now that carbocation has 1, 2 carbon groups attached to it. It's got a third bond, but it's still hydrogen. So this is still a secondary. Okay, so there's no improvement. In the carbocation stability here. So this is not going to be a valid rearrangement. Okay, if you move the hydrogen on the bottom right up here, this is going to be a primary carbocation, and that's really unstable. So that makes it even worse. Okay, so we've rearranged, and now we have a tertiary carbocation. We've done our loss of the leaving group, right? That's how we generate the carbocation. And then the next step is nucleophilic attack. And right, I said that our nucleophile is water. And so nucleophile is going to attack the new carbocation, right? So the bromide that left was on this carbon, okay? And now that carbon has the hydride that's migrated, okay? So the nucleophile is attacking a different carbon atom than the leaving group was on originally, okay? So immediately after the nucleophilic attack, we have that molecule, which is charged because the water, the two hydrogens on the water molecule, are still attached to the oxygen. They've just been dragged along as the bond is formed. Okay, so our positive charge now on the oxygen. And then the last step is a proton transfer, where we use another water molecule, another nucleophile, that instead acts as a base. And pulls a proton away from the oxygen. So that's our product. If we compare the carbon skeleton of the starting material in the product, it's the same, but the attachment point where our substituent is different. And that's because of the carbocation rearrangement. So whenever you see a reaction, like for example, if I give you the starting material and the product, and you look at the position of whatever substituent is on there and you see that it's changed, that is a major red, or I don't know if it's a red flag or a green flag, depends on which mechanism you find easier, I guess. But that should tell you, oh, okay, a carbocation rearrangement must have occurred at some point because the substituent has moved positions. Of course, it's changed what substituent it is, but it's moved positions. Now, that doesn't mean that whenever you have an SN1 reaction, you will see the substituent move to another place. Because you can have an SN1 reaction without a carbocation rearrangement. But if you have a carbocation, if this happens, then you must have had an SN1, not an SN2 reaction. Okay, so that's what it looks like in SN1. Let's do the same chemicals, only an E1 reaction. You might ask, how do I know whether it's going to be an SN1 or an E1 reaction? I'm going to show you a chart that has all of that information, cheat sheet stuff in a moment. Okay, for an E1 reaction, we start out the exact same way as an SN1, and that is with loss of a leaving group. Now, we have a secondary carbocation. Can this rearrange? Yes, this is what we just did. We already know how it's going to rearrange. Okay, I haven't explicitly drawn out the hydrogen, and that's okay. It may help you to see things if you draw it out explicitly. But this hydrogen has moved here, and now this carbon is the one that's electron deficient with a positive charge. Okay, so this is now tertiary, and then a rearrangement. Okay, so this is identical to what we just did with the SN1. The difference now between SN1 and E1 is that our water is going to act as a base for elimination rather than a nucleophile for substitution. So when we're doing an elimination reaction, unless we have tert butoxide, the bulky base, unless we have that bulky base, we're going to want to generate the most substituted alkene. Okay, so we have two options for where to deprotonate. We can do it there or there. Okay, it has to be immediately adjacent to the carbocation, again, the new carbocation. And we're going to pick the one that will give us the more substituted double bond. Is that the top or bottom hydrogen? This hydrogen is attached to a carbon with one substituent. This hydrogen is attached to a carbon with two substituents. So it's going to be the one on the bottom. Deprotonate that hydrogen, and then the bond that was holding the hydrogen onto the molecule comes down to form a double bond. and that is our alkene elimination product. Now, you might say, well, hang on, why didn't we just skip the carbocation rearrangement and use water to deprotonate here and then just have this form the double bond? And the answer is that technically does happen, but the carbocation rearrangement happens so quickly that this is the mechanism that it takes. So, in other words, the carbocation rearrangement will always happen if it's possible. And as soon as it becomes possible, it will happen. In other words, as soon as you form a carbocation, not just in this chapter, but in any chapter or any part of organic chemistry, you need to immediately say, okay, can this rearrange? Can it increase its stability? Now, carbocations will not rearrange if the stability will stay the same. So, for example, this pink example, you might say, okay, well, shouldn't we expect half of it to be one way and half of it to be the other way? Now, it turns out these two molecules are identical to each other, but that may not be the case. And for purposes of this class, if our rearrangement goes from secondary to secondary, we're going to say that it doesn't happen at all. Okay. But in this example, we go from secondary to tertiary. That is an improvement. And so because that carbocation rearrangement is valid, it will always happen, and you always have to draw it first before you can do anything with the elimination business.
Is there a reason that you wrote OH2? Like, could it be OH3?
Yes, you could write H3O plus, which is really what it is, but just showing the bond explicit. Also, I ignored the bromine after it came off, and that's fine. You can do that. Okay, questions on what carbocation rearrangements look like in SN1 and E1 mechanisms? Okay, if you have Blackboard, in the resources section, you should see yeah. Okay, you should see this chart, or two charts. This will be given to you on the exam. And this is how you're going to decide when you see a reaction, what type of mechanism is going to happen. So the first thing has to do with nucleophiles and bases, whether they are strong or weak. Okay, so all of these molecules can act as nucleophiles or as bases, but which they are, strong or weak, is going to determine what kind of mechanism will happen. So eventually you'll get to where these are like pseudo memorized, but you'll have access to this chart, so no reason to go out of your way to memorize them. Let's see. So very common ones: hydroxide, methoxide, ethoxide. Those are strong bases and strong nucleophiles. Weak bases, strong nucleophiles, like these are common and they're really varied, probably the most varied. So the halogens are in there, I minus and Br minus, cyanide, ammonia, thiols, and stuff like that. The only weak nucleophile strong base that we're going to talk about is tert-butoxide. That's the bulky one. And let's see, we start to use this chart. In fact, weak nucleophile strong base is here. So those are all E2 reactions. Okay, so when you see tert-butoxide, that is essentially just telling you that an E2 reaction is going to occur. Okay, and then weak nucleophiles, weak bases are water and alcohols. Now, notice that these are very similar to these, right? So R could be any group, so R could be methyl or ethyl. And in that case, methanol, MEOH, looks a lot like methoxide, MEO minus. Okay, so you need to make sure that you notice whether your nucleophile is negatively charged, like hydroxide, methoxide, ethoxide, or is neutral, because that's going to make a difference between it being strong or weak. Okay, so once you've determined what your nucleophile slash base is for the reaction, then you can look at the substitution level of the substrate. So do we have a primary alkyl halide, secondary, tertiary alkyl halide? And then you have your answer, basically, what type of reaction will happen. Now, if I give you an example, and this is actually changed. So you should see SN1 or E1 for this one. That's what the version online should say. Anyway, so for these two that are SN1 or E1, I'm not going to ask you to pick between those two. If that opportunity comes up, I'll just tell you what type of reaction to draw. All right. Okay, one final thing is on the leaving groups themselves. So in the examples that I've shown you, we've used chloride, bromide, and iodide at some point, I think. And these are good leaving groups, obviously, because I've shown you them acting as leaving groups. Are we missing a halogen? Yeah. So fluoride, F minus, is a poor leaving group. Okay, this has to do with the strength of the carbon-fluorine bond. Part of the reason why Teflon is so heat resistant and why fluorocarbons persist in the environment. Fluoride is a poor leaving group. Okay, and so it will not undergo any of the reactions that we've talked about in this chapter. So if I write something like this, you might say, oh, okay, well, we have sodium cyanide, which is Na plus and Cn minus. Okay, so Cn minus is a weak base strong nucleophile, so that's here. Okay, and we have a primary alkyl halide. Okay, so that should be SN2, right? Okay, so we're going to do an SN2 reaction. No, because fluoride is a poor leaving group. And so you would expect an SN2 reaction to occur, but because it's a fluoride, nothing. Okay, so as soon as you see that fluoride, well, that actually makes your life easier. Okay, so that's the halogens. I know this chapter is called alkyl halides, mostly because we've just been talking about chlorine, bromine, and iodine leaving groups. But there's other groups that can function like halogens in this particular case. Alcohols are poor leaving groups. There's a lot of things that are poor leaving groups, but okay, so if we have an alcohol and it can be treated with cyanide and we say, okay, it's going to go and undergo an SN2 reaction. No, because an alcohol is a poor leaving group. Okay, it doesn't come off the molecule very well. However, you can make them into good leaving groups. So one way to do that is to protonate them. So do an acid-base reaction. So if we take any acid, here I'm using H3O plus. There's a couple ways we could write this. We could just say H plus, or we could specify what acid, so like hydrochloric acid, for example. And we do an acid-base reaction here. And we get an OH2 plus. Okay. This is essentially a water molecule that's ready to fall off. Okay. So now this is a good leaving group. Okay, we call it water. I know it's positively charged and water is not positively charged, but after it leaves, it will become water. Okay, so now we can use our nucleophile, whatever we like, maybe cyanide. Okay, and this will undergo an SN2 reaction to give us our desired nitrile, which is the organic version of a cyanide, and water. Okay, so the other way you'll see this written is in one arrow with two steps. Maybe like this. Okay, so if you add numbers to your reagents, you can show a stepwise process just more conveniently. And so this implies that you know about this middle step happening, right? So you do H3O plus first just by itself. Envision what that is, and then take that and then add sodium cyanide, and then we get to our product. Okay, but same reaction as above. All right, so protonating alcohols makes them into good leaving groups. You can also turn it into what we call a tosylate. Okay, tosylate has the symbol OTS instead of OH. And, well, it's really OTS minus, but whatever. And the tosylate group is this. Okay, this is a molecule of toluene, which is sort of where the name comes from. And then we've got the sulfur atom kind of looking like it's sulfuric acid a little bit. And then the O minus, which is this O minus. Okay, and if we can swap an alcohol out for this group, we can make it into a good leaving group. Now, I know that okay, we've just done a completely different reaction and made a good leaving group. But this is quite commonly done in organic chemistry. So here's our alcohol that we want to do some chemistry with. To turn it into the tosylate, we use tosyl chloride, which is just a convenient version of the tosyl group. Okay, and that replaces the hydrogen on the alcohol with the tosyl group. That's a good leaving group. And now we can do just what we did above, which is add a nucleophile. Doesn't have to be. Let's do something other than cyanide. Let's do ethoxide. Okay, and so that swaps our tosylate group for our ethoxide group. I should note that now that I've done this example, the oxygen is different here. Okay, so I'm not going to ask you to draw this first mechanism, but here the tosyl chloride doesn't contain the oxygen atom of the tosylate. It gets formed sort of on the molecules. But then when we do the SN2 reaction, right, this oxygen is the nucleophile, so this attacks. Let's draw it. There we go. There's our SN2. Okay, and so the oxygen that's now attached to the organic molecule is the one with the ethoxide, and it's just dragged the ethyl group along with it. And the tosylate OTS minus falls off.
Where's the hydrogen and the chloride bond? Are they just like?
Yes, so you have hydrochloric acid. So minus HCl. In practice, what you actually have to do is get rid of the HCl before you can add a basic nucleophile. But that's lab stuff for another day. Speaking of lab, let's do a lab example. So a third of you have already done this lab. The others, you'll do it either this afternoon or tomorrow. But in the lab, what is it, lab 6 or 7? It's lab 6. So lab 6 is SN1 or SN2. Okay, part of the challenge is you got to figure out which mechanism it goes by. So you're going to be given one of 4 unknowns. Let's say we have mm-hmm. Yeah, let's say we have tertiary pentanol. So I think in the lab, this is tert-amyl alcohol. And let's see, what do? We treat it with sodium bromide and sulfuric acid. And you're going to drop put the sodium bromide in with the alcohol and then drop the sulfuric acid in through the condenser. So we have So this sodium bromide is just Na plus Br minus. Okay, so Br minus, that's our nucleophile, right? Let's look at our table. Hello. Br minus. Okay, weak base, strong nucleophile. Weak base, strong nucleophile. Yep, so that's this category here. Substrate. Okay. Primary, secondary, or tertiary.
Second.
Tertiary. So this is a tertiary alcohol. In fact, that's where the tert amyl comes from. Tertiary amyl alcohol. Okay, so SN1, right? What's the first step in an SN1 reaction? Loss of a leaving group to form a carbocation. Do we have a good leaving group? No. Uh-oh. What do? So this is where the sulfuric acid comes in, and this is why you have to add sulfuric acid to this reaction to get it to work. We're gonna it's this. We're gonna do this just with an SN1. Okay, so the first step, H3O plus, right? That's just our sulfuric acid. And so we're going to turn the OH into a good leaving group by protonating it and making it a water molecule. Okay. Then we lose a leaving group. I'm giving you all the answer to the questions. Oh, well. Okay. Now everybody's going to try to figure out which one is tertiary amyl alcohol, and you'll try to pick it, but I don't remember which unknown number it is. Okay, so we get our carbocation, right? We've lost our water by water. And now our nucleophile, the bromide, can attack. Okay, and so the boiling point density of that alkyl bromide, so this is now tert amyl. Amyl bromide. The boiling point density of that are known, and so you can distill it or put it in the volumetric graduated cylinder and measure the density, all that sort of stuff. Okay, for the other alcohols, well, some of them are SN1, some of them are SN2. For the ones that are SN2, we still have to do this protonation process, okay? Because both SN1 and SN2 and E1 and E2 require a good leaving group, okay? So if you're going to do an SN1 or any of these reactions on an alcohol, you have to do one of these two steps to make it a better leaving group. We could have done the tosylate, but that would take an extra week. So, okay. Questions on making, excuse me, alcohols into good leaving groups? Be very careful when you're dripping in the sulfuric acid. It's very exothermic. Okay. I have just, as in like a few minutes before class, posted problem set 7. Just two questions, but it's parts A, B, and C of each one. The first one is to predict the product and draw the mechanism. Okay, so that's basically the entire chapter in, all of the concepts combined into one problem. There's lots of those for you to do. And then number 2 is propose reagents. Okay, so I'm giving you the starting material in the product, and I just need you to give whatever reagent, water, methanol, sodium cyanide, anything like that, what you would actually put in the flask in order to do those reactions. As I'm seeing this, there's one thing that I kind of glossed over, and I should not do that. So let's look at, sorry, the nucleophile base chart. This work. So on the strong base, strong nucleophile section, there is RLI. Okay, we haven't talked about organolithium reagents very much. Okay, and so RLI this is just carbon bonded to lithium. Okay, so if we have, did I talk about butyllithium? Am I gaslighting myself? I don't know. Okay, so if we have carbon bonded to lithium, it essentially functions as a carbanion. Okay, the bond between the carbon and the lithium's a metal, right? So that bond is extremely polarized to the point where it's essentially a carbanion. And that is our good nucleophile. So in the same way that an SN2 reaction using hydroxide as a nucleophile, you'll end up with a hydroxide attached to your molecule. If you do a reaction, an SN2 reaction, or any nucleophilic substitution, with a butyllithium or any organolithium reagent, the nucleophile is just the carbon atom of that organic group. So let's do oh man, 2B is one of the ones you're supposed to do. Oh, here we go. 1N. Okay. So we have a tosylate, right? This is both of our new things from today. We have a tosylate, and we have I chose butyllithium because it's one of the most common ones, but butyllithium. Okay, so this is just a butyl anion with a lithium cation that we don't care about. Okay, whenever you see those metals, we're kind of going to ignore them. All right, and then we have tosylate, a good leaving group. Okay, and well, we should probably, I don't want to erase my stuff, but if you go on the chart of nucleophiles and bases, the RLI, organolithium reagents, were in the strong base, strong nucleophile. If you have a strong base, strong nucleophile, and you have a secondary alkyl halide, what kind of reaction is that? SN2. Right? Doesn't say E2, does it? Does it say E2? All right, we'll do an E2. I don't really like that, but is that actually what it says? Ugh. Oh yeah, it's too strong of a base. Where's my? Let's save it. Thank you. Okay, so in this case, because we're doing an E2 reaction, our nucleophile is going to act as a base. Okay, fortunately, our molecule is symmetrical. And so it doesn't matter if we choose hydrogen on the left or the right. What is that blue thing? Thank you. Okay, so take our base, grab the hydrogen. It's an E2 mechanism, so everything happens in one step. we form pi bond, and we have loss of a leaving group. Okay, so there's our double bond. Our tosylate has left. Okay, and additionally, we now have the hydrogen attached to that butane molecule with, if you really want, Li plus, and those are the products of that reaction. However, if I just ask you to draw the major organic product, I'm just looking for cyclohexene. Stop. Okay. Okay, because I wanted to do an SN2 reaction, let's do an SN2 reaction. So what do I want to do? We'll do this. Okay. So there, now we have, instead of a secondary, a primary tosylate, and as our lithium, we'll use this. Okay, because we have a primary alkyl halide, it's not an alkyl halide anymore, but it's going to act the same way. Because we have a primary substrate, now we actually are going to do an SN2. Okay, so for SN2, nucleophile, how do I want to draw this? Is that how I want to draw it? Doesn't really matter. Okay, so we're going to go for that carbon. It's our nucleophilic attack. And then loss of a leaving group. Okay, so now we formed, the first arrow here is the important one. We formed a bond between carbon and carbon. All right. So it might be helpful to count your carbons here. Okay. So we don't lose track of them, because not every bond is to carbon. Okay, so we've got a total of 8 carbons. One, two, three, four, five, six, 7, 8. Okay, so the bond that we formed is there. Okay, that left part is from the substrate. And the part on the right is the 4-carbon chain from the organolithium nucleophile. Would you actually do this reaction in practice? No, you would just go to the oil distillery and buy some of that hydrocarbon. But in principle, you could do this. All right. Let's do one of these. Other than A, B, and C, does anybody have a request?
F.
F. Good. Okay. F. All right. So let's kind of do let's do that same carbon chain thing that we did. And let's look for the carbons. So those are the carbons from the starting material, right? We had a bromine that was going backwards, okay? That has been replaced with an oxygen coming forwards, all right? What kind of reaction that we learned about does that? Switches the stereochemistry. The first one, yes. SN2. Okay, so I'm not requiring you to write what type of reaction it is, but it's a good practice because that couldn't possibly be on the exam. So we've done an SN2 reaction. We've swapped the bromine for... What happens when I... Oh man, I thought that was rainbow color. I'm sad now. Okay. Okay, so we have swapped the bromine for this. Okay. So all we need to do, right, and the bond is being formed to the oxygen between the carbon and this oxygen. Okay. So that oxygen needs to have our negative charge. And the way that you would actually have this is probably as a sodium or potassium salt. So you could write it like that. Or you can just write the sodium directly next to the oxygen as if it were like a hydrogen or something. What is that blue line doing? Go away. Thank you. Okay, that happens to be sodium acetate. But this is one of our, let's see. On the chart, that would be the RCO2 minus nucleophile. Okay, that's because our R group is this methyl group on the end. The CO2 is this carbon with the two oxygens. And then the minus charge, I just drew the minus charge. Currently it's, we've shown the cation directly attached to it, so we don't see the minus charge.
So which answer would you want for the?
Oh, I didn't draw the mechanism, did I? Did I ask to draw the mechanism? No, I didn't. Sorry. Yes, proposed reagents. So I would just be looking for that. So that or that's fine as well. If you don't include the charge and you don't include the counter ion, that's wrong. Okay, so that would not be a correct answer.
And bromine just went away, or we wouldn't.
Correct, and that's that would be another side product out there, which you wouldn't need to draw in this case.
We do more.
Sure, which one?
Mhm.
E? Didn't give myself enough space. All right. Hang on. Weak base, strong nucleophile, right? Weak base, strong nucleophile. Uh-oh, I think I have to edit this again. Dang it. Okay, I know what I'll turn this into. Okay, it will work with this. Okay. So we've gone from the chlorine going back to SET, so sulfur with an ethyl group coming forward. So we've swapped the stereochemistry. So this has to be an SN2 reaction. And okay, everything in the product stays the same except the chlorine, and attached to that we have the ethyl thioether, SET. Okay. So what we need for the nucleophile there is just SET minus, or we could have Etzna, I guess. Okay, so we could draw that with an anion, or actually, if you go and look on the chart of things that will do an SN2 reaction to secondary alkyl halide, you could also have just the SH without the sodium. So that is these work. So we're looking at this and that right there. Let me remind myself to change that. What about G?
Oh, no reaction.
No reaction, yeah. Okay, so we've got the fluoride there, which is if you get an F on the exam, that's bad. So fluorine's not bad. But in these cases, fluorine is a bad leaving group. Okay, so there's no reaction here, no mechanism, no nothing. Okay, any one last one? Anyone? J? J, cool. Okay, you thought you were done drawing chairs? Sorry. All right, so we have CH3ONA. All right, so we can ignore the sodium and say, all right, this is just CH3O minus. And now we need to look on our chart to see what sort of reaction this is going to do. Okay, so we've got CH3O minus. This is also MEO minus. Okay, and we have, what is this? A secondary alkyl halide. Okay, so we have methoxide, strong base, strong nucleophile, strong base, strong nucleophile, and we have secondary. So it's an E2 reaction. Okay. When we're doing an E2 reaction, we have to think about if our base is tert butoxide, sorry, that's kind of hard to see. If our base is tert butoxide or not, and it's methoxide in this case. Okay, so we don't have a bulky base. And that means we're going to generate which alkene, the more or the less substituted alkene in this reaction. So in fact, let's draw both of those. Okay. So if the carbon that the bromine is on has to be involved in the double bond, okay? So it can either go that way or that way. Usually we like to draw them inside the ring, but it would look kind of ugly over there. So outside is fine. Okay, so the first alkene, what is this mono di tri tetra substituted? How many substituents do we have coming off of that CC double bond? 2. Di substituted? What about the bottom one? Tri substituted. Okay, so this is the more substituted alkene. That's the product that's going to be formed. Okay. Ah. Why did I draw the O as a superscript? To make the less substituted alkene, we would need potassium tert butoxide. Okay. So what is the mechanism? Well, we have to remove the bromine and we have to remove the hydrogen that was on this carbon that's got the methyl group going straight up. Okay, so we need that hydrogen explicitly drawn. So we're going to use, you can draw it from any part of this that you like. So grab the hydrogen. That's ugly. That's uglier. Can I have smaller, please? Oh my God. Thank you. Be precise with your arrows, right? Okay, so that second part, the little arrow is the elimination, making the pi bond, and then we have loss of the leaving group. So when doing any of these, really any of this stuff in this chapter, the first thing you want to do is go to the chart. Okay, because there's no point drawing mechanisms or trying to predict products before you know what type of reaction is happening.
And the answer,
The answer is in the chart. Sorry, that's not what you were asking.
the final, what you said.
Okay, what do you want us to write for the final answer? That is that. Not the try. You don't need to try. One important thing is that often when I give you the reagents, I'll write them like this, where the cation is just smushed directly onto the nucleophile. In order for that for the mechanism to be drawn correctly, what you can't do is take pen, please. Pen, please. Try and take electrons from there and start drawing mechanism arrows. Okay. You need to draw the nucleophile in its charged form because when you go to either make a like do the substitution for an SN2 or SN1 reaction, you don't have the cation, the sodium, hanging on to it like it kind of looks like it's doing. So you want to make sure you rewrite without the cation. The reason I give it to you with the cation is because that's what you actually buy in the bottle and put into the reaction. It's also because it's more work for you, but okay. Questions on chapters, this is chapter 7 now, it's chapter 5 and 6. Okay, I will say the exam has a heavier focus on this last chapter. There's I was about to open it up and look at it. It's what is it? 5 pages, not like 5 sides. It's 100 points as usual. You'll have the whole time. You can bring your molecular modeling kit, but I don't know if it's going to be as helpful on this exam. Yeah, there will be mechanisms. I think there's 2 mechanisms you have to draw. Oh, yes, Tuesday. More questions?
So you moved it up.
That's
No, it's when it's on this, whenever it is on the syllabus. Okay, I didn't. Yeah.
Are you given the PKA chart?
Yes, good point. So you'll have the pKa chart, the periodic table, and the nucleophile chart that I just showed you today. Yep. All right, I will see you on Tuesday.
I just.